In mathematics, we often have to make new definitions so that we can solve problems that at first glance do not seem to have a solution. I'm going to lead you through a sequence of simple problems that demonstrate this technique. So suppose we wanted to solve the equation x minus 2 equals 0. It should be clear that x equals 2, and that's a very simple problem. But I'd now like to solve the problem x plus 2 equals 0. You will probably immediately say that x is equal to negative 2. But at some point in time in history, there were no such things as negative numbers. Somebody had to invent the idea of a negative number so that we could represent the idea of taking away 2 units. Now, if we look at the problem 2x minus 1 equals 0, you immediately might say to yourself, well, x is equal to a half. But at some point in time, there were only whole numbers. There were no such things as fractions. Somebody had to come up with an idea that, say, if you had a whole pizza, that you could cut that pizza into 2 pieces, and that this shaded area would represent a half. And thus rational numbers were born. Now suppose you wanted to solve x squared minus 2 equals 0. So in other words, x squared is equal to 2. Well, you could, for example, say that x is equal to plus or minus the square root of 2. But at some point, there was no such thing as irrational numbers or the square root of 2. This was actually the source of much debate amongst the Greeks. There was clearly the idea that the square root of 2 existed because if you had a triangle with length 1 on both legs and it was a right triangle, then the distance here would have to necessarily be the square root of 2. So the square root of 2 had some sort of use and context. But until they decided that these irrational numbers existed, then this concept didn't exist. We had to invent the idea of irrational numbers. Well, finally, we can get to this problem that says that x squared plus 1 is equal to 0, or x squared is equal to negative 1. But as you know, you cannot take the square root of a negative number. There's no such thing as the square root of negative 1. So there is no real solution to this problem. In fact, if you make a graph of this problem, you'll see that the parabola represented by x squared plus 1 never touches the x-axis, so there are no roots to this polynomial. But what if we invented a new definition, a definition for the number square root of minus 1, and we gave it a name? And that's exactly what happened. We gave the square root of minus 1 a name, and that name was I. And this introduces the idea of what are called imaginary numbers and complex numbers. So we're going to talk about complex numbers in order to lead you to the idea of solving differential equations using complex numbers. So complex numbers are numbers that are written in the form z equals a plus bi, where a and b are both real numbers and I is the square root of minus 1. So the idea is that a complex number has 2 parts, a real part, which we'll call A, and an imaginary part, which we'll call B, that gets multiplied by I. So we are going to start with this kind of new number system, and then we immediately want to understand some properties of these new numbers. So I'm going to start with 2 numbers. I'm going to call the first one Z, which is just A plus BI. And then the second number I'm going to call W, which is going to be C plus DI. And a good question is, can I add 2 complex numbers together? What is Z plus W? Is that a complex number? Well, I can take A plus BI plus c plus di. I'm going to assume that addition is commutative here, so that gives me a plus c plus b plus d times I. And a plus c is a real number, and b plus d is a real number, and so z plus w meets the definition of a complex number. So if we want to do subtraction, we just use the same idea. We can do subtraction for those two numbers, in which case we would do a plus or minus c, and then b plus or minus d. But those are both going to be real numbers, and so subtraction works as well. Can I multiply two complex numbers together? What would z times w be? Well, it would be a plus bi times c plus di. Now, I'm going to assume that multiplication works the same way as it does for real numbers so that I can distribute. So I'm going to do a times c plus b times c times I plus a times d times I plus b times d times I squared. And I'm going to recognize that I squared, because I is the square root of minus 1, has to be minus 1. So that means that my number can be written as AC minus BD, and that's the real part, plus BC plus AD times I, and that's the imaginary part. And so I can multiply two complex numbers, and they do meet the criteria of the definition of a complex number. Now, one operation that you might not be familiar with is the complex conjugate. So the complex conjugate of a number z is going to be, we're going to call that z bar. And z bar is going to be a minus bi. So this is the number that corresponds to z where we have flipped the sign of the imaginary part. Now, it might not be immediately apparent why we would need such a number, but we're going to move on to the idea of division to see why we might need that complex conjugate. So, can I take z and divide it by w? Well, that's going to be a plus b times I divided by c plus d times I, and it's not immediately apparent that we can split this up into a real part and an imaginary part. So what I'm going to do is I'm going to multiply the top and the bottom by the complex conjugate, c minus di. Now, the reason that I'm going to do that is that when I look at the denominator, I'm going to get c squared plus cdi minus cdi plus minus di squared. And what I want you to notice is that cdi and minus cdi cancel, and I squared is minus 1. And so the denominator here is going to be real. It's going to just be c squared plus d squared. So we're learning that if you multiply a complex number by its complex conjugate, then you're going to get a squared plus b squared, and that's going to be a real number. Okay, so what's going to happen with the numerator here? Well, we're going to get AC, and we're going to get AC plus BCI minus ADI minus BDI squared. And so I can actually break that up into its real and imaginary parts. So the real part here on the numerator is going to be AC plus BD, again, because I squared is minus 1. And then the imaginary part, if I factor out an I, is going to be BC minus AD. And now you can see I have a real number plus I times another real number. And so I've met the criteria for the definition of a complex number. So addition, subtraction, multiplication, and division all hold. Let's move on to some more properties about complex numbers. Complex numbers can be plotted using what is called the complex plane. And the idea is that you have the real number line, and that makes the real axis, but you also have an imaginary number line, so multiples of the unit of I that form the imaginary axis. And so what we do is we plot complex numbers in the complex plane. So if we're looking at the number a plus bi, we think about it as being the coordinate a, b. So these numbers are often basically plotted like you would plot a vector, say the vector ab. Now, because we're plotting these numbers as ordered pairs in a plane, that means that there's more than one representation for complex numbers. The representation that I've been using, z equals a plus bi, is rectangular coordinates, but we could also represent using polar coordinates. We could think about a complex number as being the distance r from the origin and an angle theta from the real line. In that case, a is going to be r cosine theta, because this distance here is r cosine theta. And then b is going to be r sine theta, because this distance here is actually r sine theta, using a little bit of trigonometry. Okay, so that means that we can think about z as being r cosine theta plus I r sine theta. Now, r, I said, was the distance from the origin. We can write r in terms of a and b. R is going to be the square root of a squared plus b squared. And then we can use some trigonometry to see that the tangent of theta is supposed to be b over a. So theta, which is often called the argument of a complex number, would be the arctangent of b over a. And so we can go back and forth between this representation in rectangular coordinates and polar coordinates. Now we can enter into one more step that will help us come up with a good notation for polar coordinates. Okay, and that is using what is called Euler's formula. So Euler came up with this idea that e to the I theta is equal to cosine theta plus I sine theta. And you might say to yourself, now where does that idea come from? Why would e to the I theta equal cosine theta plus I sine theta? But I believe that since you have all taken a Calculus 2 course, that you could actually show that this is true. And the way that you would show that this is true is to look at Taylor series. Or in this case, since the Taylor series is going to be centered at x equals 0, we would call them Maclaurin series. What you could do is you could write out e to the I theta using its Taylor series, and then write out what cosine theta is using its Taylor series, and I sine theta is using its Taylor series. And you could show that this equality holds. You might remember that e to the x as a series has lots of terms that are x to the n over n factorial. And cosine and sine also have those terms, but cosine has all the even terms, and sine has all the odd terms. And there's some weird alternating that goes on. And so if you write out each of these terms for these series, I think that you will see, once you start looking at powers of I, that you will be able to get this equality to be true. Now that we have Euler's formula, then what we're going to do is we're going to write any complex number as r e to the I theta. Because as you can see, z can be written as r times cosine theta plus I sine theta. But Euler's formula tells us that cosine theta plus I sine theta is actually e to the I theta. So the polar form of a complex number is often written as r e to the I theta, where r is going to be, again, the square root of a squared plus b squared. And theta is going to be the arctangent of b over a. And that gives you a little bit of an introduction to complex numbers and polar coordinates. I'm going to leave you with a little comic from XKCD, just to add a little bit of humor to the end of this video.